All right, so we are done with example number 1, Dr. Zeppo's class in the 7th grade of 70. Then we are done with example 2, where we use the data set from Parenthood to analyze Danny's sleep, and we used the number 8 in our hypothesis. And we wanted to know in that second example for Danny's sleep if there was evidence that on average Danny gets less than the recommended 8 hours of sleep per night. So we wrote that hypothesis as the one-tailed test. And the null hypothesis was that the mean is greater than or equal to 8, and the alternative hypothesis that we were interested in was that the mean is less than 8. And in our sample mean for the second calculation, we had a sample mean in our descriptive statistics calculated as 6.97 hours with a standard deviation equal to 1.02. And so there was sufficient evidence that the population mean is less than 8 hours, and our t-value was negative 10.19, 99 degrees of freedom, p-value less than 0.001, and our confidence interval was reported as negative infinity, 7.13. So let's finish up here. We're on the bottom of page 7. So we need to go over the assumptions of the one sample mean t-test. So we alluded to this at the beginning of this chapter 9. The assumptions of the one sample t-test are the same as they were in the one sample z-test. Excluding the assumption of the known population standard deviation. So then this leaves only 2 assumptions for the one sample mean t-test. So normality and independence. So in terms of normality, we're still assuming that the sampling distribution is that normal bell curve. Recall that we learned about the central limit theorem in the past, which that basically told us that the sampling distribution for a mean will be normal if the population is normal, or if the sample population is sufficiently large. So in practice, we don't know if the population is normal, but if the sample is approximately normal, we usually say that that's good enough. There are some ways to statistically test for normality, but we're going to get to that in a later lesson. So our preference is usually to just make a histogram and then to visually inspect the histogram. And then that second part of our assumption was independence. So once again, we do have to assume that the observations in our sample are generated independently of one another. So we can see the earlier discussions, review those earlier discussions about the z-test for the specifics. So let's go back and just review that. And we'll insert that right here. So when we were doing the Z like zebra test, the z-test had the 3 assumptions of normality, independence, and that we know the standard deviation. So with the z-test, the normality, the z-test assumes that the true population distribution is normal. This assumption is often reasonable and can be checked if there are any concerns about the validity. For the z-test, z like zebra, with independence, the second assumption of the test is that the observations in the data set are not correlated with each other, okay? They're not related to each other in any way. This isn't as easy to check statistically. It relies a bit on having a good experimental design. So you have to ask yourself if it's really plausible to imagine that each observation is a completely random sample from the population that you're interested in. And then what is not true in the t-test is true in the z like zebra test. So in the z-test, z like zebra, there is the known population standard deviation assumption. So the third assumption for the z like zebra test is that the true standard deviation of your population is known to the researchers. This assumption for the z like zebra test is typically unrealistic though, because in a real-world data analysis, it is highly unlikely that we would know the standard deviation of our population while being completely ignorant about the mu or the mean. Therefore, this assumption would almost always be incorrect, but it is the third assumption for the z like zebra test. So let's go back to the bottom of page 7. And so again, we're going to go through these assumptions of the one sample mean t-test, T like Tom. So again, we did talk about this with the z-test, z like zebra. So the assumptions of our one sample t-test are the same as they were for the one sample z-test, excluding the assumption of the known population standard deviation. So we're just left with two assumptions of the one sample mean t-test, T like Tom. So we're assuming normality and we're assuming independence. So the normality, we're still assuming the sampling distribution is that normal bell curve. When we learned about the central limit theorem, the sampling distribution for a mean was said to be normal if the population is normal or if the sample size of our population is sufficiently large. So in practice, we don't know if the population would be normal, but if the sample is approximately normal, then we usually say that that's good enough. There are some ways to statistically test for normality, and again, we're going to cover that later. So the preference for now will be to make a histogram and to visually inspect the histogram. And then with independence assumption, once again, we have to assume that the observation in our sample is generated independently of each other, and that there is no connection, no correlation, no association. So overall, these two assumptions, they're not terribly unreasonable, and then as a consequence, the one sample mean t-test is pretty widely used in practice as a way of comparing a sample mean against a hypothesized population mean. And so now we're at the top of page 8 and we're going to pause there. And then next we're going to talk about the two independent sample means t-test or the student t-test.